Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Why are there different types of planets? Imagine looking up at the night sky and realizing that the tiny points of light that fascinate us are only part of a much larger cosmic story. Around many of those stars, and in spectacular variety around our own sun, worlds form that are as different from one another as deserts are from oceans. Some are rocky and dry, others are shrouded in thick, crushing atmospheres. Some are tiny and cold, others bloated and blisteringly hot. The reason for this staggering variety does not come down to a single cause. It is the result of a grand interplay between physics and chemistry, timing and chance, the environment where a planet forms, and the chaotic ways in which young planetary systems rearrange themselves. To understand why planets come in different types, we need to follow their story from the dust that orbits newborn stars to the complex, often violent histories that shape their final appearance. Planet formation begins in a cloud of gas and dust. When a patch of that cloud collapses under gravity to form a new star, it almost always leaves behind a flattened, rotating disk of leftover material called a protoplanetary disk. This disk is not uniform. It has a temperature gradient that decreases with distance from the newborn star, pressure bumps and eddies, and regions where solids like ice and rock condense and stick together more easily. These local conditions determine the raw materials available to assemble planets and influence how quickly they can grow. Close to the star, it is hot and volatile materials cannot condense. Only refractory solids such as silicates and metals remain solid, so the building blocks of planets near the star tend to be rocky. Farther out, the disk is cool enough for volatile compounds like water, methane, and ammonia to freeze into solid ice, enriching the mass of solids and allowing bodies to grow larger more quickly. This simple difference in temperature with distance creates a first major division in planet types: rocky, terrestrial worlds near the star, and ice-rich bodies farther out. Mass matters. The mass that a growing planet accumulates deeply influences its composition and fate. Small bodies may assemble into terrestrial planets with thin atmospheres, primarily acquired from volcanic outgassing and fragile capture from the surrounding disk. More massive cores have a different destiny because they can pull in and retain the surrounding hydrogen and helium gas long before the disk dissipates. If a planetary core grows quickly enough and reaches a critical mass while the gaseous envelope is still present, it can trigger runaway gas accretion and become a gas giant. Gas giants are mostly hydrogen and helium, with cores that might be rocky or icy, wrapped in layers of metallic hydrogen in thick molecular envelopes. The timing of core growth relative to the lifetime of the gaseous disk therefore determines whether a planet remains rocky, becomes a gas dwarf with a modest hydrogen envelope, or balloons into a massive gas giant. The composition of the material in a protoplanetary disk is another critical ingredient. Not all disks are created equal. Stars locked within dense clusters and those formed from chemically enriched interstellar clouds may host disks with differing amounts of heavy elements, often called metallicity by astronomers. Disks richer in heavy elements will supply more solids, accelerating the formation of massive cores. That makes gas giant formation more likely around stars born in metal-rich environments compared to metal-poor ones. Similarly, the abundance of specific volatiles influences the makeup of planets formed in different regions. In disks with abundant water ice, the outer parts are primed to form large, icy planetesimals, and protoplanetary cores that can become gas giants or ice giants. In disks where certain volatile reservoirs are depleted, the same radial distances might yield planets with less volatile content and different surface and atmospheric chemistry. Migration changes everything. Young planets do not always stay where they formed. Interactions with the gas disk can cause nascent planets to migrate inward or outward. Even after the Q has dispersed, gravitational interactions between planets can fling them into new orbits, sometimes violently ejecting one planet while leaving another stranded close to the star. Migration explains many oddities we observe in other planetary systems. Hot Jupiters, gas giants that orbit their stars dangerously close, could not have formed in place because the inner disk was too hot and lacked sufficient solids. They likely formed far from their stars where ices were available, grew massive, and then migrated inward through the disk or via interactions with other bodies. This migratory behavior creates planets in locations that would otherwise be surprising and can strip or alter primordial atmospheres and surfaces, further diversifying planetary types. Stellar properties shape planetary destinies. The mass, luminosity, and activity of the host star determine the disk temperature profile, the lifetime of the gaseous disk, and the radiation environment that affects planetary atmospheres. Massive hot stars produce intense ultraviolet radiation and stellar winds that can dissipate disks faster, leaving less time for gas accretion and skewing planet formation towards smaller, rocky worlds. Low-mass stars have protracted disk lifetimes and strong magnetic activity that can, depending on circumstances, either assist or obstruct the growth of certain planet types and also heat and strip atmospheres after formation. A planet forming around a bright, short-lived star will face different challenges than one forming around a long-lived, dim star. The diversity of stars across the galaxy therefore seeds diversity among planets. Atmospheres are the great sculptors of planetary appearance and climate. An atmosphere can be a thin veil or a crushing blanket of gas hundreds of times denser than Earth's. The composition, thickness, and temperature of an atmosphere determines surface conditions and separates seemingly similar planets into different classes. Planetary atmospheres arise from multiple sources. They can be primary atmospheres captured from the surrounding nebula during formation, secondary atmospheres released by volcanic outgassing, or atmospheres that evolve through chemical reactions and loss processes over billions of years. Light gases such as hydrogen and helium escape more easily from low-mass planets, while higher-mass planets can retain thick primordial envelopes. Stellar radiation and particle winds can strip atmospheres, especially in planets orbiting close to active stars. Meanwhile, chemical reactions, condensation of volatiles into clouds, and interactions with a planet's surface and interior can alter an atmosphere's composition dramatically. These atmospheric processes explain the difference between a small rocky planet with a tenuous atmosphere and a larger world that becomes an enveloped mini-Neptune. Internal structure and heat sources add another axis of variety. Planets are not merely passive balls of matter. Their interiors are dynamic. Radioactive decay, residual heat from formation, and tidal heating from gravitational interactions generate internal energy that can drive mantle convection, plate tectonics, and volcanic activity. A geologically active planet can recycle volatiles, maintain a magnetic field through a dynamo process in a molten core, and renew surface features that spread or erase the imprints of impacts. Tidal heating can pump enormous energy into a moon or planet that orbits close to a massive companion, producing subsurface oceans on icy moons or extreme volcanic activity, as seen in our solar system. The presence or absence of internal heat and geological activity significantly affects planetary atmospheres and surface conditions, contributing to the diversity of observed planet types. Distance from the star determines more than temperature. It also dictates the kinds of materials that can exist on a planet's surface and in its atmosphere. Within the inner regions of a system, refractory minerals dominate, and any volatile compounds vaporize into gas or are lost. Farther out, ices and gases freeze onto solids, creating the conditions for massive icy bodies and giant planets. The location relative to key condensation fronts, sometimes called snow lines, is essential. The water snow line, where water transitions from vapor to ice, concentrates solids and facilitates rapid growth of planetesimals. Other snow lines for carbon monoxide and carbon dioxide occur farther out. A planet forming just beyond a snow line will have access to a sudden abundance of solid material and may become substantially more massive than a neighbor just inside the line. These sharp compositional transitions leave imprints on the types of planets that emerge at different orbital distances. Collisions and giant impacts are messy creators of diversity. Planet formation is a violent process filled with collisions between planetesimals, embryos, and protoplanets. A single giant impact can strip away an atmosphere, alter a planet's rotation, strip a mantle to expose a denser interior, or create moons from the debris. Our own moon likely formed from such an impact that reshaped Earth. Differences in collision history can explain why some planets have massive moons while others do not, why some retain thick atmospheres and others are stripped down to bare rock, and why some spin rapidly with large axial tilts while others are more sedate. Randomness in the timing and severity of impacts means that even planets forming in similar environments can end up very different. Magnetic fields protect atmospheres and influence space weather interactions, further differentiating planets. A planet with a strong magnetic field can shield its atmosphere from stellar winds and charged particle stripping, preserving volatiles and enabling long-term stability of an atmosphere. Planets lacking a sufficient dynamo may suffer gradual atmospheric erosion if subjected to sustained stellar activity, leading to barren surfaces. Magnetic fields also interact with charged particles to create aurora, and in some cases can funnel energetic particles into the atmosphere, driving chemical changes that alter atmospheric composition. Thus, internal dynamics that permit a dynamo not only shape the interior but also the long-term atmospheric fate. Planetary system architecture and the presence of distant stellar or planetary companions create additional complexity. Binary stars, for instance, can strip disks, truncate them, or stir them into eccentric orbits, impeding the smooth formation of planets or encouraging the formation of planets in unusual configurations. Wide-orbiting giant planets can gravitationally sculpt the distribution of smaller bodies, clearing regions, trapping objects in resonances, or scattering material inward where it becomes available for planet formation. The arrangement of planets can therefore be as decisive as local conditions, either promoting orderly growth or driving chaotic rearrangements that produce unusual planetary types and orbital behavior. Chemistry and temperature determine surface states and appearances. For planets with surfaces, whether that surface is covered by rock, metal, ice, or oceans depends on both composition and temperature. On a planet where temperatures permit liquid water and where water is abundant, oceans may form and drive climate systems and erosion that change the landscape. On colder worlds, water will be trapped as ice, perhaps forming thick icy crusts hiding subsurface oceans warmed by internal heat. Hotter worlds may host molten surfaces or exotic mineral vapors in the atmosphere. The specific chemical inventory, the relative amounts of water, carbon, nitrogen, sulfur, and other elements, determines the types of clouds that form, the colors and spectra of the atmosphere, and the kinds of surface minerals that dominate the landscape. Two planets at similar distances from their stars might still differ dramatically if their initial chemical compositions diverged. Observational perspective and bias shape how we classify planets and perceive their diversity. For many years, our knowledge of planets beyond the solar system came from methods biased toward specific types of planets, those close to their stars or those massive enough to produce detectable signals. The transit method favors large planets in short orbits, while radial velocity detection favors massive planets whose gravitational tug on their stars is measurable. As a result, when exoplanet discoveries first proliferated, hot Jupiters seemed common, skewing early impressions of what planetary systems look like. As techniques improved and missions probed different parameter spaces, the true diversity emerged, revealing abundant small worlds, sub-Neptunes, super-Earths, and multiple systems with architectures very unlike our own. Our growing observational toolkit continues to broaden the planetary menagerie we can detect, reminding us that apparent distributions are influenced by how we look. Planetary evolution adds time as a crucial factor. A planet's type can change over its lifetime. Young planets often look quite different from their older selves. A small planet might accrete a thick atmosphere early on, only to lose it due to stellar radiation, turning a mini Neptune into a bare rocky super-Earth. Conversely, a planet suffering heavy bombardment might later generate a significant secondary atmosphere through volcanic outgassing. Tidal interactions can cool or heat planets, alter rotation states, and drive internal restructuring over geological timescales. Planets orbiting stars that become more luminous over time will experience shifting habitable zones, altering the prospects for liquid water on their surfaces. Thus, the category a planet fits into today might not reflect its origins or its ultimate fate. Complex feedbacks can create surprising outcomes. For example, greenhouse gases can trap heat and maintain habitable surface conditions. But runaway greenhouse effects can also lead to scorching, uninhabitable worlds. Conversely, high albedo clouds or ice can reflect stellar light and cool a planet. Interactions between atmosphere, surface, and interior can create stable climates or lead to runaway states. Planetary magnetic fields, atmospheric chemistry, and surface oceans can together foster or hinder conditions favorable to life, and those interactions are sensitive to initial conditions that vary widely across the galaxy. Such feedback processes multiply the ways in which similar starting conditions can diverge into different planetary outcomes. Moons and rings extend planetary variety. Satellites can be major actors in the evolution of planets. Large moons can stabilize a planet's axial tilt, moderating seasonal extremes and contributing to climate stability. Moons can also be sources of tidal heating for themselves or for their host through resonant interactions, as seen in the volcanic activity on certain moons. Rings can indicate recent collisions or ongoing processes of debris trapping and can obscure or modify the radiation environment around planets. The existence and character of moons and rings are shaped by collision histories, capture mechanisms, and the dynamics of the surrounding system, adding layers of complexity to planetary diversity. Exoplanet discoveries have forced us to broaden our classification schemes. Before other planetary systems were known, categories were largely derived from the solar system: terrestrial planets, gas giants, and ice giants. Exoplanet surveys revealed intermediate types such as super-Earths and mini-Neptunes that fill the gap between Earth and Neptune in mass and size. These new classes challenge simple divisions and suggest that planetary formation is a continuum with many branches. Some planets blur categories: rocky worlds with substantial envelopes of light gases, or icy bodies with thin hydrogen atmospheres. The richness observed prompts more nuanced frameworks that consider composition, structure, atmosphere, and formation history, rather than simple size-based labels. Atmospheric escape and photoevaporation shape planet populations, especially close to their stars. High-energy radiation from a star can heat and strip a planet's atmosphere, especially when the planet is small or at close orbital distances. This process can hollow out certain regions of planetary parameter space, producing gaps in the distribution of planet sizes and compositions. Observationally, the signature of photoevaporation appears in the relative scarcity of planets with certain radii at certain orbital periods. Atmospheric escape can thus transform a gas-rich world into a rocky remnant, creating an evolutionary pathway that contributes to the diversity we observe. Plate tectonics and surface recycling are not universal, and their presence or absence changes planetary destinies. On Earth, plate tectonics drives carbon cycling between the surface and interior, moderating climate over geological timescales and maintaining habitability conditions. On other planets, stagnant lid tectonics, episodic resurfacing, or wholly different interior behaviors could produce climates that evolve in dissimilar ways. Whether a planet's interior conditions permit plate tectonics depends on its size, composition, thermal history, and the presence of water as a lubricant in its mantle. Such geodynamic diversity explains differences in surface features, atmospheric composition, and long-term climate stability across planets. Chance and chaos are ever present. The combined dynamics of disk turbulence, stochastic collisions, and gravitational interactions ensure that chance plays a substantial role in determining planetary outcomes. Two systems with very similar initial conditions can evolve into very different configurations simply because of the timing and specifics of a few key interactions. This inherent unpredictability means that diversity is not merely an outcome of initial conditions, but of the complex, chaotic processes that follow. Chance events can determine whether a planet migrates inward, suffers a stripping impact, or retains a life-friendly environment. Planetary classification benefits from multiple perspectives. Astronomers classify planets by observational properties such as mass, radius, and orbital period because these are measurable. Planetary scientists classify by composition and internal structure to reflect formation and evolution. Astrobiologists focus on surface conditions and atmospheric chemistry to determine habitability potential. Each perspective highlights different aspects of planetary diversity and underscores the many dimensions along which planets can differ. A comprehensive understanding requires integrating these viewpoints, acknowledging that a single planet may sit in multiple categories depending on which features one emphasizes. Looking ahead, new observations and theoretical advances will deepen our understanding of why planets are so diverse. Missions that characterize atmospheres through spectroscopy will reveal the chemical fingerprints of many worlds, exposing trends in atmospheric composition, cloud properties, and surface conditions. Direct imaging will let us see planets in wider orbits and study their colors and reflected light. Improved models will connect disk physics to planet demographics, helping us trace back observed varieties to specific formation pathways. As our census of planets expands across different stellar types and environments, patterns will emerge that help explain how frequently different formation outcomes occur and under what conditions specific planetary types arise. In the end, the existence of different planet types is a natural consequence of a universe governed by a variety of physical laws and initial conditions. Varying temperatures and compositions across disks, differences in disk mass and lifetime, the timing of core formation relative to gas dispersal, migration and dynamical interactions, collisional histories, internal heat and magnetic protection, and the influence of the host star all converge to produce a spectrum of planetary outcomes. Chance and chaos amplify small differences in initial circumstances into the profound variety that telescopes now reveal. Diversity is not a glitch in the cosmic plan, it is the plan. Appreciating this diversity enriches our understanding of the Earth too. By seeing Earth alongside the full cast of planetary types, we learn which of our planet's features are common and which are rare. We begin to identify the processes that maintain a stable climate and the fragile balances that allow oceans and life to persist. Comparisons with other planets sharpen our appreciation of the role that factors such as a protective magnetic field, plate tectonics, and a favorable amount of water play in shaping habitability. Meanwhile, exotic worlds provide natural laboratories to test the limits of planetary physics and chemistry. Worlds with supersonic winds, with vaporized rock in their atmospheres, with deep, high-pressure ice mantles, or with oceans warmed by tides instead of starlight. Each new discovery adds a data point to the tapestry of planetary evolution. To summarize without reducing the richness, planets differ because the conditions of their birth and their subsequent histories vary across many axes. Temperature gradients in disks set the initial materials available. Disk mass and chemical composition govern how fast cores can grow. Stellar properties influence disk lifetimes and radiation environments. Migration and dynamical interactions relocate planets and reshape systems. Collisions, internal heat, magnetic fields, atmospheric processes, and chance events combine to sculpt final appearances. Observational bias and evolving measurement techniques shape our perception of which types are common. As science advances, so will our understanding of how all these risk factors combine to produce the breathtaking diversity of planetary worlds. The story of planetary diversity is ongoing. Each new telescope and instrument peels back a layer, revealing worlds that challenge our preconceptions and expand the palette of possibilities. From tiny molten rocks skimming their suns to enormous gas giants parked in lonely, distant orbits. From ocean worlds hidden beneath icy shells to compact systems filled with closely packed super-Earths, the galaxy is a grand experiment in planetary formation. Understanding why different types arise helps us decode that experiment, revealing the physical laws at work and the role of chance in shaping worlds. It shows us that the planet we call home is one among countless variations, a product of its local environment, history, and a string of fortunate circumstances that allowed it to become habitable. In that realization, there is both humility and wonder, and a strong impetus to keep looking. Even within a single planet type, variety blooms from subtle differences. Two terrestrial planets may both be rocky and solid, yet one may possess sprawling continents and dynamic oceans, while the other lies airless and crater-scarred. Venus and Earth illustrate this vividly. Their masses and sizes are so similar that they are often called planetary twins. Yet one is a temperate water world supporting life and complex ecosystems, while the other is a furnace cloaked in a suffocating carbon dioxide atmosphere with clouds of sulfuric acid. This divergence arose from variations in atmospheric evolution, volcanic outgassing, solar radiation, and the presence or absence of surface water. It reminds us that classification is a starting point, not a limit, in understanding the unique paths planets can take. The presence of water, whether liquid, solid, or vapor, is especially influential. Water participates in chemical reactions, shapes geology through erosion, regulates climate through the water cycle, and may be a necessary ingredient for life. Some planets form with abundant water ice, storing oceans beneath frozen exteriors. Others lose their water early due to intense stellar heat or never acquire much in the first place. The quantity and state of water therefore creates another branch in planetary diversity, distinguishing desert worlds from ocean worlds and icy crusted spheres from planets with warm open seas. As more distant exoplanets are studied, scientists expect to find planets fully enveloped in global oceans, lacking any land at all, or worlds where water exists only as transient vapor on the sunlit side, redistributing heat in strange atmospheric cycles. Climate stability is a fragile property that only some planets manage to preserve across geological epochs. Feedback systems like the carbon silicate cycle regulate carbon dioxide levels and surface temperatures on worlds with both volcanism and liquid water. Without such stabilizing processes, a planet may slip into permanent icehouse or greenhouse states, narrowing the range of surface conditions that remain habitable. Climate instability can transform one type of planet into another entirely, locking in a new identity that persists for billions of years. We see this in Mars, which likely possessed rivers and lakes long ago, but lost most of its atmosphere and water, transitioning into a cold desert. A planet can therefore begin its story as one type and end as another, shaped by climate evolution. In addition to volatile substances like water, the distribution of carbon and nitrogen plays a central role in planetary chemistry. Carbon chemistry can give rise to diverse atmospheres, from methane-rich hazes on distant icy worlds to carbon dioxide-dominated atmospheres like those of Mars and Venus. Nitrogen, meanwhile, can form thick backgrounds for atmospheres as on Earth and Titan, enabling complex photochemistry and potential biological pathways. Worlds where these elements are scarce will exhibit profoundly different atmospheric behaviors and surface properties. Subtle differences in elemental ratios may determine whether clouds are made of water droplets, methane crystals, sulfur aerosols, or exotic compounds yet to be detected. Gravity dictates how planets hold onto their atmospheres and shape their own interiors. A more massive planet exerts stronger gravitational pull, compressing its inner layers into high-pressure structures. Deep within giant planets, hydrogen is squeezed into exotic phases like metallic hydrogen, generating strong magnetic fields. Meanwhile, small bodies fail to retain heat and collapse into airless, geologically inactive stones. Gravity also sets escape velocities for atmospheres. If a planet is too small, its gases evaporate into space over time, reducing any atmosphere to a tenuous film or removing it altogether. The boundary between retaining and losing gases establishes a continuum that stretches from Mercury, essentially a naked rock, to Neptune-like worlds wrapped in deep, insulating gaseous blankets. Not all worlds orbit in the gentle circular paths we see in our solar system. Many exoplanets are found on eccentric orbits that swing them between scorching heat and freezing cold. Such dramatic environmental swings can push planets into unique atmospheric states, causing periodic condensation, sublimation, or collapse of the entire atmosphere. A planet might transition from one atmospheric regime to another depending on its position in orbit. Some could have seasons so extreme that gases freeze out of the air and then return as vapor later in the orbit. Orbital eccentricity therefore raises new classes of climate behavior far beyond the mild seasonal rhythms of Earth. The tilt of a planet's rotation axis introduces another dimension of diversity. Axial tilt regulates the severity of seasons. A world with no tilt experiences minimal seasonal change, potentially locking its climate into static patterns. A planet with extreme tilt may undergo drastic shifts in climate, with entire poles pointed toward or away from the star for long stretches, boiling one hemisphere while freezing the other in alternating epochs. Tilts can be modified by past impacts or by gravitational nudges from neighboring bodies, meaning the same planet might evolve through multiple climate modes over its lifetime. Such changes redefine the environmental character without altering the planet's core structure. Rotation speed plays a key role in atmospheric circulation and magnetic field generation. Rapidly rotating planets spawn fierce jet streams and banded cloud structures, as seen on Jupiter and Saturn, while slow rotators like Venus experience sluggish circulation with long days and nights tied closely to atmospheric tides. The dynamo effect that powers planetary magnetic fields also depends on rotation, helping determine whether the atmosphere will remain shielded or exposed. The duration of day and night affects how heat is distributed, whether one side bakes and the other freezes, or whether winds spread warmth more evenly. Rotation alone can make two planets of similar composition feel like entirely different worlds. Surface texture and crustal type amplify distinctions. A world covered in smooth lava plains differs tremendously from one sculpted by mountains, shifting dunes, or icy chasms. The thickness of a planet's crust, the amount of internal heat pushing upward, and the presence of erosion all determine surface roughness in geology. Gas-covered worlds lack true surfaces accessible to observation, hiding their solid cores beneath layers of fluid. Ocean planets may have high-pressure ice phases beneath their waters instead of rocky seabeds. Even the concept of a surface becomes ambiguous when atmospheres become so deep and dense that there is no clear boundary between air and ground. Radioactive isotopes present at birth help define the thermal lifespan of a planet. If a planet forms in a region enriched with long-lived radioactive elements, its interior can remain hot and active for billions of years, sustaining volcanism and perhaps plate tectonics. Others born with lower initial abundances may cool and harden early, shutting down the internal engines that refresh surfaces and recycle atmospheres. This silent internal factor creates yet another fork in the paths planets may take, leading to vastly different geologic destinies, even from similar starting sizes. Planetary rings can hint at evolution through tidal forces, collisions, or shepherd moons. A ring system may be temporary, continually replenished by shattered moons or captured debris. Their existence suggests ongoing dynamical interactions and can influence the environments of any nearby moons through shadows, radiation reflection, and material exchange. Rings add to the environmental identity of a planet, especially visually, but also physically, altering how radiation and charged particles behave around the planet. When planetary systems include numerous close-packed planets, as discovered around many red dwarf stars, gravitational interactions can become exquisitely delicate. Tiny shifts in mass or orbit can destabilize entire systems, leading to dramatic rearrangements where planets trade places, collide, or are thrown outward into interstellar space. Such rearrangements build further planetary diversity by subjecting worlds to new radiation environments and orbital distances that differ drastically from their formation zones. A planet's current location sometimes tells only the final chapter of a much longer and turbulent story. Habitability adds a special lens through which we view planetary diversity. The term does not mean that life exists, but that conditions might support liquid water on the surface in stable climates, at least long enough for life to arise. The so-called habitable zone around a star depends on luminosity, atmospheric composition, and planetary feedback processes. Yet even planets within this zone can become uninhabitable if they lose their atmospheres, freeze completely, or enter runaway greenhouse states. Meanwhile, worlds outside the traditional habitable zone may still harbor life in subsurface oceans warmed by tidal forces, expanding the concept of habitability far beyond surface water. Thus, the search for life pushes the classification of planets into new directions not captured by classical categories. Tidal forces deserve deeper appreciation. They shape bodies not only through heating, but by altering orbits, spinning planets down, and locking them so one side eternally faces the star. Tidal locking produces severe day-night contrasts, with one hemisphere blistering under constant light, while the other remains in unbroken cold darkness. Atmospheric circulation on such worlds becomes radically different from that on Earth, potentially producing thick clouds on the day side and frigid deserts on the night side. These worlds might still support habitable conditions in a twilight belt between extremes, again demonstrating how different planet types arise from orbital geometry alone. The discovery of rogue planets, worlds drifting through space without a star, pushes diversity to the cosmic frontier. These planets may have been ejected from their systems or formed directly from collapsing clouds without ever lighting a star. Without stellar warmth, their surfaces would be frozen, but internal heat or insulating atmospheres could maintain oceans beneath thick ice shells. These dark wanderers represent a type of planet not bound to any system architecture at all, reminding us that planetary identity is not always tied to a star. Planetary atmospheres also evolve chemically through interactions with life, where life exists. On Earth, billions of years of biological activity have transformed our atmosphere, filling it with oxygen and enabling the ozone layer that shields the surface from harmful radiation. Life as a planetary process can therefore alter classification, distinguishing a biologically modified world from a sterile one. If life is common in the universe, then some planets will become shaped by biology in ways we cannot yet fully imagine, adding entirely new branches to the planetary family tree. The methods scientists use to interpret atmospheric spectra continue to improve, allowing them to detect molecules at ever smaller concentrations. Each chemical detection adds texture to our understanding of that planet's type and reveals processes that may be shaping its fate. Clouds, hazes, and aerosols complicate this picture, sometimes hiding deeper layers or altering observed colors. As instruments sharpen, more planets will move from vague labels to richly detailed identities based on their full atmospheric and geophysical profiles. Ultimately, planetary diversity reflects the creative power of cosmic evolution. From the collapse of molecular clouds to the turbulent adolescence of young planetary systems, physics pushes matter into countless configurations. Gravity pulls matter together. Heat sculpts interiors. Radiation strips atmospheres. Chemistry paints surfaces. And chaos decides winners and losers in orbital rearrangements. The result is a galaxy, and likely a universe, filled with worlds so varied that our taxonomy can barely keep up. Each time we discover a planet that defies expectations, it forces us to expand the rules, update theories, and embrace a broader understanding of what a planet can be. It may be that no two planets in the universe are exactly alike, just as no two snowflakes share the same pattern. Diversity is not merely an outcome, it is an inevitability of nature working with a rich set of ingredients and physical processes. In this grand context, the question, why are there different types of planets, becomes a celebration of complexity. Planets differ because the universe is dynamic, matter is versatile, and countless influences interact over time. Differences in formation environments, migration histories, chemical inventories, sizes, distances, stellar influences, internal processes, and random events all combine to generate a cosmic spectrum of planetary possibilities. Diversity is the rule, similarity the exception. Our expanding catalog of planets encourages humility regarding our place in the universe. Earth is not the template for planets, it is one example among uncountable others. Its traits, liquid water oceans, breathable atmosphere, protective magnetosphere, active geology, represent a fortunate convergence of circumstances rather than standard planetary outcomes. Recognizing this enhances our appreciation not just for the complexity of other worlds, but for the rarity and preciousness of our own. The more planets we study, the more we see that nature loves experimenting. It shapes worlds from the same basic raw materials, but each time the results differ depending on timing, physics, and chance. Giant planets of scorching clouds, super-Earths wrapped in thick hydrogen veils, frozen dwarfs of pure ice, volcanic moons glowing like embers, ocean globes reflecting starlight off endless seas, planets so dark they swallow nearly all the light that hits them, planets so bright that clouds of reflective crystals make them shimmer like jewels. This is the diversity that emerges from cosmic creativity. As future observatories map more exoplanets, analyze their atmospheres, and maybe even glimpse their surfaces, our picture of planetary diversity will sharpen. Some questions will find answers, new ones will appear. And as humanity eventually reaches outward across the solar system and perhaps to nearby stars, we will witness other planets up close, feeling their gravity under our feet and observing their horizons firsthand. Those experiences will deepen our understanding even further and reveal subtleties impossible to detect from afar. In the end, the universe does not build worlds with a single blueprint. It builds them with freedom. Diversity arises because nature explores every possibility available to it, and because even tiny variations in conditions can produce wildly different results over time. That is why there are different types of planets, because the cosmos, from its earliest moments, has been a masterful artist, painting the galaxy with worlds in every shape, size, color, temperature, orbit, and destiny imaginable. And with every new discovery, it invites us to continue the journey of understanding, marveling at the endless ways gravity and stardust can become a planet. The diversity of planets does not stop with the well-known worlds or the categories humanity has already established. The universe is not limited by our imagination, and each time astronomers discover something unusual, it pushes us to rethink what a planet can be. Maybe someday we will have entirely new classes of planets based on exotic chemistry, strange orbital arrangements, or energy sources we have not yet considered. Imagine planets made mostly of plasma with electromagnetic storms replacing weather, or worlds that float freely through space powered by internal nuclear reactions, or planets formed around dead stars where gravity warps light into spirals. These might sound like science fiction today, but before the first exoplanets were found, worlds outside the solar system were fiction too. Science evolves with discovery. As we continue to explore the reasons behind different types of planets, it becomes clear that planets are not accidental objects. They emerge from the laws of physics interacting with matter in a cosmic dance billions of years long. Size governs internal pressure, which controls heating, which determines chemistry. Chemistry determines what molecules exist and what state of matter dominates. Gravity shapes structure, layers, atmospheres, and moons. Distance from the star influences temperature and energy. Time allows worlds to change from one form to another. Every planet is the result of branching choices driven by physics, and those choices lead to the incredible diversity we see. Learning why planets differ also tells us something profound about ourselves. Earth once formed from the same cosmic dust as every other planet. At one time, Earth could have become a mini Neptune, shrouded in hydrogen. It could have dried into a scorched desert like Mercury. It could have frozen into a lifeless ice world like Europa. But the combination of mass, distance, atmosphere, geology, and stabilizing moon allowed Earth to become a place of liquid water and living organisms. When we ask why there are different types of planets, we are also asking why we exist at all. A planet like ours required many coincidences coming together. Understanding planet types helps us investigate one of the biggest mysteries in science. How common is life in the universe? A gas giant is unlikely to host life on its cloud tops, though some extreme possibilities exist. A tidally locked world might have a narrow habitable strip. Water worlds could hide flourishing biospheres beneath ice where sunlight never reaches. Rogue planets might harbor subsurface oceans warmed by radioactive decay. Each type of planet offers a different environment, a different set of chemical opportunities, and a different story. By mapping planet types and their conditions, we can narrow down where life could be found and which worlds deserve further exploration. Future telescopes will sharpen this quest. With space observatories capable of reading the thin signals of planetary atmospheres from across the galaxy, scientists will look for signs of habitability and perhaps even signs of biology. We will not only classify planets by size or composition, but by potential. Worlds that might support ecosystems, climates that resemble Earth's, or chemical cycles that could lead to life. The simple question of why there are different kinds of planets becomes the doorway to searching for neighbors in the cosmos. The journey to classify planets is still young. Even in our own solar system, several bodies blur traditional lines. Pluto, Eris, Haumea, Makemake, and their icy cousins in the Kuiper Belt are neither typical planets nor mere asteroids. They represent a new type of object formed in the cold outer frontier. Ceres, in the asteroid belt, has signs of past water activity and may one day be classified differently if we find internal oceans. Moons like Titan, Europa, and Enceladus have the ingredients of habitability, making them planet-like in importance. Some astronomers argue that classification by orbital status misses the scientific richness of worlds that are geologically active and chemically complex. In the future, we may classify planetary worlds more by what they are than where they, but as definitions evolve, new categories will emerge, just as dwarf planets did in 2006. Much of planetary diversity also arises from chaotic events. Collisions do not just form planets, they remake them. Earth's moon-forming impact stripped away our early atmosphere and changed our rotation. Uranus, tilted sideways, may be the result of a huge blast early in its history. Mercury's large iron core suggests it lost its rocky mantle through a giant collision. Mars may have once been on track to become more Earth-like, but was stunted as a neighboring protoplanet stole some of its material. Even small gravitational nudges over millions of years can reshape a planet's orbit, altering its climate forever. A world on the edge of habitability can become frozen or scorched by a tiny shift in distance from its star. Diversity is written into the violence of young star systems. There is also the role of chemistry beyond Earth-centric assumptions. Planets far from their stars can preserve fragile molecules that would normally break down in heat. In colder zones, methane can act like water, forming lakes, clouds, and even rain as it does on Titan. In hotter regions, rock vapor might form cloud layers and rain molten minerals in fiery storms. Exotic atmospheres of neon, carbon monoxide, or sulfur could exist on planets orbiting stars with extreme chemistry. Where oxygen dominates, rusting rocks and blue skies become possible. Where hydrogen rules, thick envelopes, deep layers, and metallic states take over. The universe allows more forms of weather, landscape, and geochemical cycles than Earth could ever display alone. Diversity in planets is a diversity in chemistry under different cosmic conditions. Another layer of difference comes from time itself. Planets evolve. A young rocky planet may be covered in magma oceans, eventually cooling into solid crust and breathable air if conditions allow. A gas giant might lose its atmosphere if its star grows too active, becoming a bare core resembling a super-Earth. A habitable planet may heat up over billions of years as its star brightens, turning lush environments into deserts or steam worlds. Planetary systems are not static. Their stars age, orbits shift, atmospheres escape, interiors freeze or fracture. A planet's type today might not be the same type millions of years ago or millions of years in the future. Even Earth, for all its stability, is changing slowly toward a time when oceans will evaporate and life will struggle to survive. The types of planets are snapshots in time, not permanent labels. Looking further into cosmic history, the earliest planets formed from materials created in massive star explosions called supernovae. Without these explosions, there would be no heavy elements, no rocks, no oceans, no life. A young universe filled mostly with hydrogen and helium may have produced very different planets than those forming today in a metal-rich galaxy. The ongoing generations of stars enrich the cosmic inventory, enabling new planetary chemistries. This means the diversity of planets is increasing as the universe ages. The first planets may have been simpler and less capable of supporting life, while later ones like Earth gained the right ingredients through cosmic recycling. We can see now that to explain why there are different types of planets, we must understand the interplay of countless forces across billions of years. Physics shapes structure, chemistry shapes composition, location shapes climate, chance shapes history, evolution shapes destiny. Every type of planet is a chapter in the story of how matter organizes itself across the universe. And that story is still being written. Even with thousands of exoplanets discovered, we have barely touched the surface of what exists. Our telescopes are best at finding large planets close to their stars, but future instruments will reveal smaller, more Earth-like worlds farther out. We may find entire families of planets we have never imagined. Super puff worlds with cotton candy densities, planets where diamond is as common as dirt, or planets with ring systems thicker than Saturn and stretching millions of kilometers. The deeper we look, the more types of planets will emerge, each one expanding our understanding of what a world can be. This knowledge also humbles us. Earth once felt like the standard for what a planet is supposed to be. Now we know that Earth may be rare, not because it is superior, but because it developed under a unique combination of cosmic circumstances. We are one example among countless possibilities. The real question may not be why there are different types of planets, but why the universe is so full of environments that can transform matter into complex structures. Diversity is not accidental. It is the natural outcome of a universe with space to evolve. As humanity explores beyond our solar system, classifying planets becomes more than an academic exercise. It guides space missions, helps us design instruments to detect life, and sharpens the search for places where humans might someday travel or settle. It helps protect Earth by teaching us how planets can fail. Studying Venus reveals the risks of runaway greenhouse effects. Studying Mars shows the consequences of losing atmosphere and magnetic protection. Gas giants warn us about radiation belts and gravitational hazards. Icy moons teach us how fragile internal heat can be. By understanding every type of planet, we better understand how to sustain our own. There is also beauty in acknowledging planetary diversity, from shimmering gas clouds swirling on Jupiter to glass-like ice plains on Pluto, from molten worlds circling too close to their stars to silent rogue planets drifting between constellations. The universe is a gallery of worlds with endless variety. Each type of planet is a work of cosmic artistry, shaped by billions of years of sculpting forces, both orderly and chaotic. Even the smallest asteroid-like body has a story written in its craters and composition. In the end, the reason there are different types of planets is the same reason there are different types of anything in the universe. Nature thrives on variety. Given enough time, energy, and ingredients, matter finds new forms, new balances, new paths of evolution. The universe does not repeat itself, it experiments. Worlds become the laboratories where those experiments play out, testing heat, pressure, chemistry, and cosmic fate in every possible combination. Human curiosity has only just begun to explore these experiments. Future generations may classify planets not just by what they are made of, but by what they could become. We might speak not only of Earth-like planets, but Earth-capable planets, worlds that could transform into habitable havens with a little guidance. We might discover planets that challenge the very definition of planet as they blur into stars or moons or something entirely new. Each discovery will push the boundaries of our understanding and expand the catalog of planetary types. One day, humans might set foot on worlds where the sky glows green with methane storms or purple with agitic gases. Children of the future might grow up knowing that planets come in more varieties than languages, and that our home is just one of many perspectives on what a world can be. This recognition can unite us with a cosmic identity. We are citizens of a universe that builds endlessly, experiments relentlessly, and never runs out of creativity. The diversity of planets shows us that we are part of a grander pattern. Earth is not alone. It is a member of a vast family of worlds. Each different type of planet is a reminder that the cosmos never settles for one design. It keeps trying, keeps shaping, keeps surprising. And as long as stars are born, as long as matter circles gravity's pull, new planets will form with new features and new possibilities. The story of planetary diversity is far from over. The universe will continue inventing new worlds, and we will continue learning from them. So why are there different types of planets? Because the universe itself is diverse, dynamic, and driven by the physics of creativity. From the smallest rocky world to the largest gas giant, from frozen exols in deep space to fiery spheres hugging their stars. Planets showcase the endless potential of matter under the influence of time, gravity, and chance. Their variety is proof that the cosmos is alive with change. Every planet adds to the tapestry of existence, and together they tell the story of how the universe explores every possibility. And perhaps the most exciting part of that story is this: the next discovery might reveal a type of planet we have never imagined. The universe always has another surprise waiting, another world forming in the dark, another clue to why creation takes so many forms. Every telescope pointed at the stars is not just searching for dots of light, it is searching for new answers to the question that brings us here. What else is possible?